For the talk now, I'm happy to invite Aviv from FordeFi. Where is Aviv?
Here.
Oh, here. We will talk about a subject we all love hearing about, breaking threshold ECDSA. So, take it, Aviv.
Good afternoon, everyone. My name is Aviv. I'm a researcher for FordeFi. And today I'll talk about two vulnerabilities that we found in Oblivious transfer libraries. First, I'd like to thank Dima, who is also here in the audience, and Ben for their amazing work on this research. So, first, what is Oblivious transfer and why do we care about it? So, Oblivious transfer is this simple yet critical cryptographic primitive where you have Alice that wants to send two messages to Bob. She wants to send one of two messages to Bob without learning which one of the two messages Bob actually receives. So we'll get into a more detailed definition later. But first, OT is used extensively in MPC protocols. So in the MPC setting, we have Alice and Bob who wants to compute some functionality over their private inputs. And the idea is that you can use Oblivious transfer to accomplish various functionalities. For example for such protocol is the multiplication protocol, where you have a secret sharing of X and a secret sharing of Y, and you want to compute a secret sharing of the multiplication. And then you can compute an even higher level protocols, like the one which we're interested in today, which is threshold ECDSA, where Alice and Bob have some secret sharing of the private key of the ECDSA. Okay, and why do we care about threshold ECDSA? Well, for one, because threshold ECDSA is used extensively in MPC wallets, alongside a growing research of making these protocols more efficient. And essentially, in recent years, almost every year saw the publication of a new threshold protocol for ECDSA. And in general, there are two approaches to construct threshold protocols for ECDSA, Oblivious transfer being one of them, and the other one is homomorphic encryption. And there are various famous protocols for each class. And while homomorphic-based encryptions have faced some significant bugs in recent years, like Bitforge and TSRock from last year, Oblivious transfer-based threshold protocols have actually grown in popularity, being simpler and perceived as more robust. So we found 3 vulnerabilities in OT libraries, and all of them were disclosed to the authors of the respective libraries. It's important to note that all of them were fixed in a very responsive and professional way. And today we will see 2 of the 3 vulnerabilities that we found that are actually used within larger threshold ECDSA implementations. So we should also note that the vulnerabilities that we found on the Oblivious transfer components of the threshold ECDSA protocol affects the overall threshold ECDSA protocol, where essentially if you manage to mount an attack on the OT component, you're then able to compromise the private key of the compromised party. So this is all to demonstrate that Oblivious transfer is not a silver bullet for threshold ECDSA, and we want to suggest that more secure implementations and standard implementations are needed for Oblivious transfer in general. And it's also important to say that the vulnerabilities that we found are in specific implementations and it doesn't imply on the security of the protocols that they implement. Okay, so we will start by giving a proper definition of Oblivious transfer, and then we will see two constructions for Oblivious transfer protocols and the respective vulnerabilities that we found. Okay, so Oblivious transfer was first introduced by Rabin in 1981. He described this protocol as a two-party protocol, where on one side you have a sender with two messages, M0 and M1, and on the other side you have a receiver with a choice bit, and by the end of the protocol, the receiver should learn the message of his choice, namely MC. And there are two security requirements for this protocol. The first one, sender privacy, which requires that the receiver doesn't learn the other message of the sender. And the second requirement, receiver privacy, which requires that the sender doesn't learn the choice bit of the receiver, and consequently he doesn't learn the output message that the receiver gets. So while this is an informal definition, the formal definition is given in the UC framework, but for this presentation we will only use the informal one. And also, like I suggested at the beginning, OT was shown to be complete for MPC in the sense that you can build like any functionality that you want. It was shown by Killian in 1988. And lastly, there are various constructions for Oblivious transfer from various asymmetric cryptographic primitives like Diffie-Hellman or RSA. And today we will see two constructions from Diffie-Hellman assumptions. Okay. So the first implementation that we will see, which is named the simplest protocol for Oblivious transfer by Choel Moladi from 2015, is based on the computational Diffie-Hellman assumption. So it will be very useful to have a quick recap of Diffie-Hellman, which I'm sure you're all familiar with. So in Diffie-Hellman, we have some acyclic cyclic group, and the generator G of that group. And the protocol begins with Alice sampling some scalar A and sending G to the A to Bob. Bob sampling some B and sends G to the B to Alice. And now they can both compute their established shared secret, namely G to the AB. And now they can use it as a symmetric key in some encryption function like AES and transfer secret messages to each other. So this was Diffie-Hellman, and now for the simplest of the protocol. So as you can see, it's a slight modification of the Diffie-Hellman protocol. But here, Alice has two messages, and Bob has a choice bit. So you can already see that Bob has a choice. He either sends G to the B or A times G to the B according to his choice bit. And Alice computes two keys, which she used to encrypt the corresponding messages. And the intuition for this is that Alice will compute her two keys such that Bob's know the discrete log of one of these values, namely among B and B over A, Bob knows the discrete log of exactly one of them. And so that exactly one of her keys will equal G to the AB, which is used, the key that Bob knows to compute, which is used to transfer exactly one message. Now let's be more concrete about it. And let's show the correctness of the protocol, namely that Bob is able to decrypt the message of his choice. So if Bob chooses 0 and sends G to the B, this means he's now able to compute K0, exactly like in the Diffie-Hellman case. And so he will be able to decrypt M0. Now, if Bob chooses 1 and sends A times G to the B, then you can see that he is now able to compute K1, so he will be able to decrypt M1. In both cases, we saw that Bob is able to decrypt the message of his choice. Okay, for sender privacy, we need to show that Bob cannot decrypt the other message of Alice. And this reduces to the fact that Bob cannot decrypt the other key in each case, which reduces to the fact that he doesn't know the discrete log of either B over A or B in each one of these cases. For receiver privacy, we want to show that Alice doesn't learn the choice bit of Bob. And this reduces to the fact that both of his messages are indistinguishable from each other. And you can convince yourself that if Alice indeed sends a valid group element, then both G to the B and A times G to the B are both uniform group elements, and as such, both values are indistinguishable. So this indistinguishability property will be very important when we move on. So let's keep it in mind. Okay, now for the first vulnerability that we found, this vulnerability were found in the implementation of the simplest OT protocol that we just saw. This OT protocol was implemented as part of the DKLS example code by the authors of the DKLS protocol. And the idea of the vulnerability is that Alice can cause Bob to leak his choice bit by sending an invalid curve element. And by doing so, Bob actually leaks his secret choice bit. And then we demonstrated that using this attack on the Oblivious transfer component of the threshold ECDSA protocol, there is an exploit that allows you to extract Bob's secret share from the ECDSA, from the threshold ECDSA protocol. So one last detail. You probably know that the groups commonly used for Diffie-Hellman are elliptic curve groups. And in elliptic curve groups, you have points with x and y coordinates from some finite field. And there is a curve equation that defines you which points are valid and which are not. And then you can define the group element over such points. And the idea is that the group operation requires you to take points that are actually on the curve. Which begs the question, what happens if you take a point which is not on the curve? Then in this case, most implementations will just return error right away. But some may still allow you to operate on such points. But the result will be that if you try to operate on an invalid point, the result that you will get is again an invalid point. Okay, so with this in mind, let's go back to the simplest OT protocol. And we remember that the protocol begins with Alice sending a group element to Bob. Now, if Bob doesn't check the validity of the point, then what will happen next is that Bob, according to his choice bit, either sends G to the B as a valid group element, or A times G to the B, which now is an operation on an invalid point by Alice, then the result will be an invalid point. So we see that in this case, Alice is able to leak Bob's choice by simply checking if the response that she gets is a valid or an invalid point. So this was the general idea behind the vulnerability that we found in the ECDSA implementation. And we should know that their implementation is actually more complicated than this. They implemented a version which they named Verified Simplest OT, which actually adds proofs of knowledge that Alice must provide to Bob along the protocol. For example, Alice must provide to Bob that the A value that she sends is the value that she knows the discrete log of. So you can already see that this introduces some complications. But at the end, we managed to find an exploit to circumvent this to circumvent this proofs of knowledge. And you can see all the details in the blog post that we will share by the end of this presentation. But now let's move on to the second vulnerability that we found. So now we see another OT protocol. In this figure, it is actually a simplified version of the Mesanr protocol from 2019. In this protocol, where you can already see that this protocol has only 2 messages instead of 3, because the idea here is that we will directly use the established keys as the output messages instead of Alice providing them as inputs. Okay, so the protocol begins with Bob, and he starts by generating 2 group elements. The first element, R prime, should be a random group element, and the other point, R, is computed as a hash over R prime times G to the B. And you can think of it like Bob is trying to mask his G to the B using the hash value. So now Bob sends both values under some permutation, and this permutation, whether he applies it or not, is given by his choice bit. And the idea is that only R will be useful to him to compute the transferred message. And now let's look at Alice's side. You can see that she computes 2 group elements, but now she knows the discrete log. Sorry, Bob knows the discrete log of exactly one of them. And then she computes her output messages such that exactly one of them will be G to the AB, which will serve as the transferred message. Okay, now this is a lot of details, but we will only need the beginning of the protocol, where Bob computes both these group elements, and we will get to this right away. But before this, we should mention that the next vulnerability that we show was found in an implementation of the DKLS 23 protocol by the Seren's Labs. And this implementation uses an implementation of the Mesanr protocol that I just showed. And the idea of the vulnerability is that incorrect sampling on Bob's side of the R prime value leads to him leaking his choice bit with a probability of 7/8. And then, like before, this attack results in an attack on the threshold ECDSA protocol that uses this implementation. Okay, so one detail before we get to the vulnerability. So their implementation uses curve 25519 for the group operations. And the cool thing about this curve is that it kind of promises you that you don't have to worry about all the invalid point stuff like the one we saw in the previous vulnerability. Actually, if you go to the Wikipedia page, you see that it says you don't need to worry about invalid points. But then there is one pitfall that we should be aware of, and it regards to the fact that this curve has a cofactor of 8, which means that the group generated by this curve is not a prime group, but rather it is comprised of a large prime subgroup and a small subgroup of size 8. And you can think of it like having 8 sets of equal sizes, where one of them being the prime order subgroup, and another 7, which are 7 co-sets of this group. And the idea is that you can identify if you get an element from one of the red co-sets, or if you get an element from the green subgroup, by taking this to the power of q and checking if you get 1. So this is some distinguishing property. You can see where this goes. So in general, if you take some 32-byte bit string, then the element that this bit string will represent is in either of these 8 subgroups with in these 8 sets with equal probability. So while this is not a problem for most applications over curve 25519, like in the Diffie-Hellman case, where the first thing that you do is to eliminate the cofactor element by taking the value to the power of 8, and then you can do all the subsequent operations in the small subgroup. So actually, in our protocol, this can be an issue. So let's go back to the Mesanr protocol. And you can see that R and R prime should be generated as random group elements so that they are indistinguishable. And if we look at the computation of R, and I'm simplifying here a bit and assuming that the hash function returns valid group elements. So you can see that R computes as a valid group element, meaning that it is in the small subgroup. But then you should also generate R prime to be a uniform element from the small subgroup. But in their implementation, what they did is that they took this R prime value to be a 32-byte bit string array, which means that with a probability of 7/8, you find this value in one of the red cosets, making it distinguishable from R. And then when Bob sends both values under the permutation, Alice can simply tell which one of them is R and which one is R prime. So in the actual threshold ECDSA protocol that this implementation is used in, what you do is that you do 256 instances of this protocol, in which Alice can learn Bob's messages in 7 out of 8 of them, which leaves only 32 bits of Bob's secret. And then she can do a brute force attack because 32 bits is small enough to allow this. And by that, she breaks all of Bob's secret bits. Okay, so to sum it up, we saw 2 vulnerabilities in this Oblivious transfer primitive. So Oblivious transfer is very important primitive, and in light of these vulnerabilities, we want to suggest that more work is needed around the security of this protocol and around the standardization of Oblivious transfer in general. And another thing is that we want to renew awareness about invalid curve points attacks, which is a quite old idea, but yet we expect these kind of vulnerabilities to still happen as long as new cryptographic primitives are being built. And lastly, for the rest of the details, you can go to this QR, to our blog post. And yeah, thank you very much. No. In both cases, the vulnerabilities are in the specific implementations. We consider, as far as we know, the protocols themselves are secure.
So how do you fix the second one? You check and you try again, or some different method?
Yeah, so To fix the second vulnerability, one thing you can do is that you can apply the two-factor clearing thing that allows you to project invalid points into the small subgroup. And there is also one detail we should say is that the hash function that we saw there also should return a valid group. So these are both things. One of them is known as two-factor clearing, and for secure hashing, it is known as hash to curve, which is also a measure that one needs to take into account.
So this is only for curve, the specific curves.
Yeah. Yeah. This issue is in this specific curve, as most other curves have a cofactor of 1, meaning they have only one prime subgroup.